Today we're doing some more Calculus 2 practice problems looking at polar coordinates. What are polar coordinates? Polar coordinates are a new way to describe a point. Instead of x and y, the horizontal and vertical displacement from the origin, we now express it as r times theta, where r is the distance from the origin to the point, the direct distance, and theta is the angle that position vector will make with the x-axis. So for example, this point right here is r distance away from the origin, right? And we can swing that vector up theta degrees or theta radians to describe that point as r theta. So how can we convert x and y, or in other words Cartesian we also call rectangular. So how can we convert these rectangular xy coordinates into r and theta? Well, we can make this triangle, right? R is the hypotenuse and x and y are the adjacent and opposite legs, and we can just use a little bit of trig. So cosine of that angle would be the adjacent over the hypotenuse, or the x over r. You can just rearrange it to solve for x. X is equal to r cosine theta. You can do the same thing with sine theta to find out y is equal to r sine theta. So we're going to use these repeatedly throughout the video to transform rectangular coordinates into polar coordinates. So let's look at an example of converting polar to rectangular. So these are polar coordinates. We know that the -2 is in reference to r, and 5 pi over 3 is in reference to theta. So what that means is we can swing around to 5 pi over 3 and then go not +2 radius, we're at a -2 radius, so we're going to swing around and make that angle, but then we're going to end up over here because of that negative radius. But how can we describe that point in rectangular coordinates? Well, x is equal to r cosine theta, so -2 cosine of 5 pi over 3 is 1/2. Y is equal to r sine theta, so it's going to be -2 times sine of 5 pi over 3, which is -√3/2. And as you can see, we ended up in about the same point at -1, not √3/2, but √3, right? So let's look at an example now of doing the same thing, converting this point 8 pi over 2 to rectangular and also plotting the point. So let's call this x. We're going to plot the point in the Cartesian plane, or with rectangular coordinates. So this is theta, right? And this is r. So all that means is on a polar plane, we're swinging up an angle of pi over 2 and then going a distance 8 from the origin. So this would be 8 pi over 2 plotted in polar, right? But we want to plot it in rectangular, so we know that x equals r cosine theta, 8 cosine pi over 2. Cosine of pi over 2 is 0. Y equals r sine theta, 8 sine of pi over 2, which is 1. 8 sine, or sine of pi over 2 is 1. 8 times 1 is 8. So this coordinate, 8 pi over 2, in rectangular is 0, 8. So we can graph that point right here, 0, 8. It ended up being the same in polar as it is in rectangular because of that angle. But it's a fairly easy process, right? So what if we're going backwards, though? What if we're converting rectangular? And now we actually have the possibility of 2 polar coordinates. Let's think back to this example up here. Was there another way we could have gotten to that same point? How about we just swing to whatever that angle this is, and now have a +2 to get there, instead of going all the way down here and then going the opposite direction with a negative radius. We could have just swung half the angle and kept a positive radius. So let's do the same thing here. These are rectangular coordinates. We want 2 polar coordinates, and they want us to plot. So the polar coordinates, let's see, how can we get to 0, -9? Well, -9 right here, right? This is 0, comma, negative 9. Couldn't we think of that as swinging a full 3 pi over 2 and then going a positive 2 radius, right? So we went a radius of 2 after swinging the entire 3 pi over 2 angle, right? Was there another way we could have done that? What if we only swing to here, right? So a positive radius here would mean we're going this way. But let's just do a negative radius. So we're going to swing to pi over 2 and then have a negative 2 radius to end up at the same point. So we're going a negative 2 radius after only swinging pi over 2. After only swinging through that angle. So those are the two polar coordinate pairs that you can make through this rectangular coordinate. This rectangular coordinate, we're able to produce these two polar coordinates. Okay, let's also look at these rectangular equations. Well, we already know that x equals r cosine theta and y equals r sine theta. So if we want to eliminate this x and y, we'll just make these substitutions. xy is the same thing as r cosine theta times r sine theta. That's equal to 4. So r squared sine theta cosine theta is equal to 4. We have now converted the rectangular equations into polar. How about this one? What about x squared and y squared? Well, we know that x squared equals r squared cosine squared theta. Y squared equals, and do we know what this equation is? Isn't this the equation of a circle? So we're going to have a cool result here. Y squared is r squared sine squared theta. So x squared plus y squared is r squared cosine squared theta plus r squared sine squared theta. 9. We can leave it like that. Well, let's do a bit more simplification. Let's factor out the r squared. We're left with sine squared theta plus cosine squared theta. And do we know what that equals? Sine squared theta and cosine squared theta equal 1, or added together equal 1. So we just have that r squared equals 9. In other words, we could represent this as radius equaling plus or minus 3, right, if we do the square root. So, and we could actually just drop the negative, because we're just making we could make a circle here. Now there's a much simpler way to describe a circle. Instead of having this equation and saying, okay, this is a circle with radius 3, now you're just given that r equals 3 and not given a theta, you can assume that that is a circle. So what if we're going the other way, converting polar equations into rectangular? Well, r equals negative 1, like I said, that's the same as r equals 1, right? It's just a circle with radius 1. So what we could do is square both sides, and then we have r squared equals 1. And then we could replace that r squared. This is now something in our toolbox. X squared plus y squared equals r squared. Now we have x squared plus y squared equals 1. So this is the equation of a circle with radius 1 in polar, which, by the way, is equivalent. This is equal to r equals 1. Because a circle with a negative 1 radius all the way around is the same thing as a circle with a 1 radius all the way around. Except this is what we're used to, the equation for a circle with radius 1 in rectangular coordinates, right? How about this one, though? R equals 5 cosine theta. How are we going to get rid of the r's and the thetas? Well, we know that x equals r cosine theta. And we want an r on each side. If we multiply both sides by r, then we have r squared. That's good. And 5r cosine theta. That's good. We can now make the substitutions. R squared is s squared plus y squared. And we know that r cosine theta is just x, right? So now we have completely eliminated all of the polar equations to make rectangular. So these are the simple operations that we do with polar, just converting coordinates and plotting them, and also converting equations back and forth from polar and rectangular. And in the next video, we'll look at area in polar coordinates. So that's how you do